Pluto, a far-off and baffling smaller planet, was once an individual member of our solar system's planetary family. However, later alarming declarations by leading astrophysicists Neil deGrasse Tyson and Michio Kaku brought Pluto back into the spotlight with a stunning disclosure. They suggested that this frosty world is on a potential crash course with Neptune. But how could this happen, and what might be the outcomes of such an enormous event? Are we witnessing an interesting cosmic phenomenon? Or is there something else to this looming infinite crash? Join us as we investigate the potential outcomes of a Pluto-Neptune collision. Pluto, a previous planet that was downgraded to a dwarf planet partly due to its curious orbit, remains a subject of interest and study in the cosmic community. According to recent predictions by leading researchers, Pluto's trajectory is perilously close to Neptune's. Leading astrophysicists Neil deGrasse Tyson and Michio Kaku are both raising the warning of a potentially dangerous crash between these two planets, which could be an immense threat to Earth. But how is such an event even conceivable? Pluto's journey around the Sun is unlike any other planet in our nearby planetary system. It requires a stunning 248 years to complete a single orbit. This means that since its discovery in 1930, it hasn't even completed one full revolution. However, the interest doesn't stop there. Pluto's path is marked by its highly elliptical shape, diverging entirely from the nearly circular orbits of the major planets. What makes Pluto's orbit even more unusual is its inclination, calculated at 17 degrees to the ecliptic plane. The path Pluto follows is much steeper compared to the other planets. This inclination and eccentricity add layers of complexity to its orbital pattern. One of the most fascinating aspects of Pluto's orbit is its convergence with Neptune's. For around 20 years in each orbit, Pluto actually draws closer to the Sun than Neptune, resisting what we might expect from their positions in the solar system. This leads to the natural question: why hasn't Pluto collided with Neptune? The answer lies in the gravitational influences of other planets. The study of Pluto's orbit began shortly after its discovery. Initially, astronomers struggled to grasp its unique path. Unlike the other planets, whose orbits lie somewhat near the ecliptic plane, Pluto's orbit stood out with its steep inclination and eccentric shape. The mystery deepened with the realization that Pluto's orbit does indeed cross Neptune's. The stability of Pluto's orbit amidst these complexities is proof of the intricacies of celestial mechanics. The three-body problem in space is about figuring out how three objects like Pluto, Neptune, and the Sun move and influence each other with their gravity. It's like trying to predict where they will go based on where they start and how they pull on one another. In Pluto's case, this problem shows how its path, Neptune's path, and the Sun's gravity all cooperate in a complicated way. Terms like asymptotic libration, scope libration, and VSK oscillation are part of this puzzle. According to astrophysicists, what's keeping all planets in their orbits is a kind of libration. Regarding Pluto and Neptune, this term means that whenever Pluto crosses Neptune's orbit, its position is always at least 90 degrees away from Neptune. This spatial separation is crucial in preventing their orbits from colliding. Scope libration, on the other hand, refers to the vertical movement of a celestial body in its orbit. For Pluto, this means that when it comes closest to Neptune or any other giant planet, it is positioned far above their orbital plane, offering an extra layer of protection from potential impacts. Another critical factor in this situation is the VSK oscillation. This is named after three researchers, VAV, Apple, LV, and Chi, who studied how things move in space. It's about how three space objects, like Pluto, Neptune, and the Sun, pull on one another with their gravity. This pulling influences how they move, and in Pluto's case, VSK helps us understand why its path around the Sun is so strange. Despite the apparent chaos, this oscillation helps keep Pluto's orbit stable for an extraordinarily long time. The VSK oscillation shows that even though things in space may seem wild and random, certain patterns and rules keep everything in place. All of these parts help keep Pluto's orbit stable, ensuring it doesn't collide with Neptune or stray off course. This three-body problem helps in understanding how these orbits change due to the way space objects pull on one another. Studying this helps us learn more about Pluto, our solar system, and distant stars and planets. Mathematical simulations in the late 1980s revealed that despite these stable properties, Pluto's orbit is actually turbulent, with minor deviations in initial conditions leading to significant differences over millions of years. However, these unusual properties of Pluto's orbit have been found to maintain stability over incredibly long timescales, effectively keeping the chaos under control. Recent computer tests have helped us understand how the giant planets, like Neptune, Jupiter, and Saturn, influence Pluto's orbit around the Sun. Neptune has a special relationship with Pluto, where for every 2 orbits Pluto makes around the Sun, Neptune makes 3. This resonance helps keep Pluto's orbit stable. However, Neptune isn't the only one helping. Jupiter's gravity also plays a large part in protecting Pluto's orbit. What's more, Saturn helps overall too. These tests show that Jupiter's gravity alone is strong enough to ensure Pluto stays on a steady path for an extremely long period, possibly even billions of years. It's as if Neptune, Jupiter, and Saturn are working together to ensure Pluto can continue to move safely in space without running into trouble. These peculiarities are vital in the larger context of the universe for maintaining the order and consistency of celestial bodies' movement. Without these components, the solar system as we know it would be a place of far greater turmoil and unpredictability. Bodies like Pluto could potentially collide with others or be ejected from their stable orbits, leading to a domino effect on other celestial bodies. For Pluto, particularly with discussions about it possibly colliding with Neptune in the future, understanding its orbit is essential. This gives us a clearer picture of the solar system's dynamic nature. The case of Pluto illustrates how even the most seemingly unstable orbits can achieve a state of balance through the complex interaction of gravitational forces and orbital mechanics. It also shows the importance of constant observation and study of these phenomena to better grasp our place in the universe. Investigating the depths of space often leads us to confront the eccentric nature of celestial bodies, and Pluto's orbit is a perfect example of this unpredictability. The concept of orbital chaos, which refers to the delicate dependence of a celestial body's orbit on its initial conditions, is clearly illustrated in the case of Pluto. This means that even slight variations in the dwarf planet's position or speed can significantly change its long-term orbit. Using virtual simulations has been incredibly helpful for researchers to figure out how Pluto moves in space. These simulations use intricate math to mimic how Pluto, along with other space objects like Neptune, pull on one another. By adjusting small details in the simulations, astronomers can see how even tiny changes can make a big difference in where Pluto ends up. In the late 1980s, these simulations showed something really interesting about Pluto's orbit. Despite having mechanisms like asymptotic and scope libration to keep it stable, its orbit can still be wild and unpredictable. If you start with even a tiny difference in where Pluto is or how fast it's moving, over many years its path can end up looking very different. However, despite this chaos, Pluto's orbit remains stable for a long time, billions of years. This means Pluto's journey around the Sun has a kind of order to it, even though it seems all over the place at first. Predicting large events, especially when they involve chaotic orbits like Pluto's, presents huge challenges. The inherent unpredictability of these systems means that long-term predictions are often filled with uncertainties. While mathematical simulations provide a strong tool to understand and predict the future behavior of celestial bodies, they also highlight the limits of our predictive capabilities. These models depend heavily on the accuracy of initial conditions and the complexity of the interactions they simulate. Any slight mistake or distortion can lead to drastically different outcomes, making precise predictions a daunting task. Furthermore, the chaotic nature of celestial orbits like Pluto's reminds us of the ever-evolving and dynamic nature of the universe. While we have made huge strides in understanding space, the case of Pluto reminds us of how our knowledge of the universe still remains limited. Understanding the gravitational influences of the giant planets on Pluto's orbit provides valuable insights into the broader dynamics of the solar system. It shows how the presence and position of each planet can have a sweeping effect, influencing the stability and trajectory of other bodies within the system. So why are prominent astrophysicists only now raising concerns about a potential crash between Pluto and Neptune, despite all these complex forces working to prevent such an event from occurring? Neil deGrasse Tyson, a renowned astrophysicist, offers a unique perspective on the mysteries of our solar system, particularly the captivating case of Pluto. Tyson, known for his role in the renaming of Pluto from a planet to a dwarf planet, offers insightful commentary on the evolving nature of celestial mechanics and the public's fascination with the unexplored reaches of space. Tyson's position on Pluto's renaming is rooted in the ever-expanding knowledge of our solar system. He sees the renaming as not a downgrade, but rather a necessary adjustment to our growing understanding of the many bodies orbiting our Sun. Tyson's approach to celestial mechanics is one of continual learning and adaptation. He views the intricacies of Pluto's orbit, as well as its interactions with Neptune, through a lens that recognizes the unpredictability of space. He suggests that while Pluto's orbit is stable for now, it could undergo significant shifts in the future. This makes the study of its trajectory particularly valuable for understanding the broader forces at play in our solar system. As he often notes, science is always evolving, and Pluto is a perfect example of how new knowledge can reshape our view of the cosmos. Tyson's concerns regarding Pluto's long-term stability stem from the ever-changing dynamics of our solar system. Despite its current stability, Tyson acknowledges that in the future, shifts in the gravitational interactions between Pluto, Neptune, and the Sun could lead to unexpected changes. The delicate balance that currently keeps Pluto's orbit steady may eventually be disturbed by changes in the Sun's gravitational influence, the movement of other planets, or even the impact of new forces yet to be discovered. Tyson's emphasis on these future uncertainties serves as a reminder that the universe is a constantly shifting system, and that even what seems stable today could change in unforeseen ways. His warning about the possibility of a collision between Pluto and Neptune highlights the evolving nature of our understanding of celestial mechanics. As we continue to study Pluto and its peculiar orbit, we must consider how the forces of gravity and the intricate interactions between celestial bodies will continue to shape the future of our solar system. The potential for a Pluto-Neptune collision may be a distant possibility, but it underscores the importance of ongoing research and our constant need to adapt our understanding of the universe as new discoveries are made. It is likely that our understanding of space, time, and gravity will continue to evolve, revealing more surprising and awe-inspiring phenomena. This is the journey that awaits as we look to the stars for the answers to questions that have long eluded us. Pluto's future might look unclear, but with each new study, we uncover more about how our solar system functions. The cosmic dance of planets like Neptune and Pluto reminds us of the immense complexity and grandeur of the universe. While it is clear that Pluto's orbit is likely to remain stable for the foreseeable future, the potential for change is always there, hidden within the chaotic nature of space. Pluto's journey through space, despite its current stability, is far from simple. As the dwarf planet, it provides a unique case study of the intricacies of celestial mechanics and the forces that govern the solar system. The fact that its orbit intersects with Neptune's without leading to a catastrophic collision challenges conventional expectations. This fascinating scenario invites further exploration of how different forces work in tandem to keep objects in space from colliding. While Neptune's gravity is often considered a dominant factor in shaping Pluto's orbit, the interactions between all of the solar system's planets, especially the gas giants, are pivotal in stabilizing Pluto's path. Jupiter, with its massive size, plays a crucial role in this gravitational dance, helping to maintain the equilibrium of the smaller, more erratic bodies in the outer reaches of the solar system. Saturn, too, with its enormous rings and gravitational pull, contributes to the overall stability of planetary orbits. These giant planets act as cosmic shepherds, ensuring that Pluto's orbit, despite its eccentricities, remains mostly free from danger. In addition to gravitational influences from other planets, the Sun's gravity remains the ultimate force shaping the trajectories of every object in the solar system, including Pluto and Neptune. The Sun's pull is the reason for the general pattern of orbits and the underlying stability of the solar system. However, the Sun itself is not static. It undergoes various cycles of activity, including solar flares and changes in its magnetic field, which could, over incredibly long periods, affect the orbits of distant bodies like Pluto. These changes, while subtle over short time frames, could potentially alter the way Pluto and Neptune interact in the distant future. The study of Pluto's orbit not only provides insight into the past and present conditions of our solar system, but it also sheds light on how planetary systems evolve over time. Although Pluto is currently safe from a direct collision with Neptune, the solar system's dynamic nature means that no trajectory is truly fixed forever. There are forces beyond gravity that influence the motion of celestial bodies. Even the tiniest perturbations in the orbits of planets can lead to larger shifts down the line. This chaotic motion is one of the fundamental characteristics of the universe, constantly shifting and evolving, presenting new mysteries for astronomers to decipher. The prediction of a possible Pluto-Neptune collision in the future, though highly unlikely in the immediate future, highlights how even stable systems can be unpredictable over long timescales. By modeling the orbits of objects like Pluto, scientists not only understand the present configuration of the solar system, but also gain valuable insights into the mechanisms that could shape the solar system's future. Simulations involving Pluto's orbit have shown that its path around the Sun is susceptible to small changes in initial conditions. These minor alterations, when compounded over millions or even billions of years, could ultimately lead to significant shifts in its orbit, potentially bringing it closer to Neptune's path. Moreover, the ongoing study of Pluto's orbit raises the question of whether other dwarf planets or trans-Neptunian objects may one day experience similar encounters with Neptune or other larger planets. The outer solar system remains a realm of great mystery, with many objects yet to be fully studied. The dynamic interactions between these bodies could reveal more about the mechanisms that govern orbital stability and the eventual fate of the solar system. Ultimately, the future of Pluto, as well as the rest of the solar system, will depend on a combination of forces: gravitational, physical, and perhaps unknown factors that scientists are still working to fully understand. The complexities of planetary motion offer a glimpse into the long-term future of the solar system, where even seemingly stable systems are always subject to change.